Bob, this is a recorded lecture. I will explain. It should be a quick lecture, inshallah. And if you have any questions, ask me please later. Okay. Let me share my screen. So I'm going to give you one problem, okay, because I haven't talked about it before, and then we'll talk about what's a thermodynamic cycle. We have an example يا شباب. عندي tank, it's insulated tank, okay, it's a rigid tank and it is insulated. That means there is no heat transfer in or out of the system, okay. So I have an insulated tank, contains water initially at 1 bar pressure. Okay, so the pressure of this water is 1 bar. Then an electrical heater with 1 ampere. So there is a current, there is electrical, electrical work with 1 ampere. So I'm applying now an electric work with the current is 1 ampere. Is applied for 2 hours. Okay, so the duration of this work applied is 2 hours until the water is completely converted into saturated vapor. Okay, so I'm starting with the initial state and the final state is saturated vapor. All right, so the question is, determine the voltage required to do the work. The volume of this tank or water is 0.1 meter cube and the mass of the water is 0.1 kilograms. 0.1 kilograms. Okay, so basically I have a tank contains water. This tank is rigid, there is no insulation, so this process is a adiabatic process. Then I'm applying an electrical work with 1 ampere current until the water becomes saturated vapor. I'm applying it for 2 hours, and the questions find or determine the voltage required to do this work. All right. So as you know, ya shabab, in electric engineering, or maybe you've taken this in the physics, we know that the work or the power is voltage times the current. Okay. And in order to find the work, right, is simply you multiply by the time and then you get the work. Or the original definition is that work divided by time. So if you divide the work by time, you get the power, right? And we know that the power is voltage times current. So basically, I have this equation now, which is W of the electrical work is minus, I'm adding minus here يا شباب ليش؟ لأنه this electric work is done on the system. So if you want to use this value for the work, it must be negative. So for example, if you have another problem where it gives you this work, electrical work, when you use it in the equation or in the energy balance, you need to add a minus. You need to add a minus. That's why I'm adding a minus here. So this electric work is minus voltage times current times the delta time. So the question is, find this voltage. So I need this voltage V. Okay. So we have another way, we have another equation that involves work, which is basically the first law of thermodynamics, or the energy balance. So if you apply the energy balance, you have delta U equals Q minus W. And this W is basically now my electric work in this process. And I know that Q, there is no heat transferring in or out of the system. So basically, my Q here is 0. Okay? So now I can write as, and this 0 minus W, so it becomes minus W equals M delta small u. All right? So, and we define that here the W is minus VIT delta time, or the amount of time duration. So simply the final equation becomes VI delta T equals M delta small u. And then the voltage becomes, the final equation for the voltage is simply mass times delta U over the current times the time. Okay? خلاص, that's it. Now you need to find value. You have M, the mass, you have the current, and you have the time, which is 2 hours. Then you just simply need to define each state and then find the internal energy at each state. So if you look at state 1 ya shabab, it's 1 bar, and I know the volume and I know the mass of the water, so I can get the specific volume, which is 1 meter cube per kilograms. If you check the table ya shabab, table A3 I believe, you will find this is a saturated mixture. Okay, so you can find the quality from the saturated mixture using the volume and the saturated liquid and saturated vapor specific volume, and we get the quality as 0.59. Then now we can evaluate the internal energy using this equation, U equal UF plus X UG minus UF. Alright, so you do this at the pressure, the 1 bar pressure. Okay, so we found U1. Now we need U2. What do we know in the second state? We know that this is a rigid volume, so V2 must equal V1. Okay, and we also know, I told you in the problem, it is saturated vapor, so that means it is the G state. Okay, so I go to table A3 and I look for 1 meter cube per kilogram in the VG. So I'm looking for 1 in the VG. I get to the VG table in the table A3, and for example, I can pick A2 or A3, whatever, it's going to be the same thing. So I reach this point. I found that I need to do interpolation because I have two values, 1.159 and 0.8857, so it's in between. So I do interpolation in order to find UG or U2 in this case for the second state. So I do this and I find U2 by interpolation to be 25.4 kilojoule per kilograms. Okay, that's it. Now I have U1, I have U2, then I can simply evaluate the voltage, 0.1 times U2 minus U1. Don't forget to multiply by the 1000, the kilojoule here, so I need to multiply 1000. Then you divide by the ampere times 2 hours, which is converted to seconds, which is the SI unit, and I get the voltage around 12 volts. Okay, so this is just an example. This is an important example to show you what is an electrical work in this case. Okay, so electrical work, you can write it as PIT or delta T in this case. The second thing I wanted to talk about today, Shabat, is what a thermodynamic cycle. I think I've mentioned this quickly in one of the lectures. A thermodynamic cycle is a sequence of processes that begin and end at the same state. Okay, so let's say start state 1 to go to state 2, state 3, and then come back to state 1. This is you completed a thermodynamic cycle. So if you apply the first law of thermodynamics for a thermodynamic cycle, because you start and end at the same state, the change of the energy of the system is zero, because the system went back to its original energy, to its original state. So that means for a thermodynamic cycle, the work of the cycle is equal to the heat of the cycle. Okay, work of the cycle equal to the heat of the cycle. Usually in thermodynamics, we try to evaluate the performance of thermodynamic cycles. And in order to evaluate the performance of a thermodynamic cycle, we basically use this ratio. So we write the desired output energy over the input energy. So desired output energy over input energy. Example of this cycle is what we call a power cycle. In a power cycle, you have a system. It's exchanging heat with two mediums or two reservoirs, we call them. You have a hot reservoir and you have a cold reservoir. So this system goes through a thermodynamic cycle, going through different states. And during these states, ya shabab, it is taking heat from the hot reservoir and dissipating heat Q out to the cold reservoir. And while doing this cycle, it actually produces a certain work. So a power cycle, like for example, in electricity power plants, where they produce energy or produce electrical energy. Okay, in these plants, they actually run a thermodynamic cycle where they produce power or they produce work from a shaft. Okay, like a gas turbine, for example, or a steam turbine. by getting energy from a hot fuel, okay, and then you have also heat dissipating to the cold side of this engine, okay, or gas turbine. So this is just a quick example for you. That's a power cycle, and is an example of a thermodynamic cycle. The objective is, what is the desired output energy here? Is I'm desiring to produce torque or work here. Okay, so this is my desired output. Now, if I wanna evaluate the performance of this cycle, I use this equation, which I call, this parameter is called efficiency. So my desired output is the work of the cycle, and my input, usually I use a fuel, hot fuel, or I want to burn it. So that's my input to the cycle. So this is Qn. All right, so this is Qn. This is my input energy to the system. So if you write, based on this first law of thermodynamics, or energy balance, the work of the cycle is equal to the heat of the cycle. So we can rewrite it as Q of the cycle. And what is the total Q of the cycle, Shabab? It's just a summation, okay? Summation of heat transfer in or out of the system, right? So in this case, Shabab, I have Qn to the system, and since Q out is negative, so I have Qn minus Q out. So Qn, so my Q of the cycle is Qn minus Q out, which is the summation of the energy heat transfer in or out of the system, or the net heat transfer in or out of the system. So this is the equation, represents the performance of the power cycle. Another example, Shabab, is what we call refrigeration cycle or heat pump cycle. Okay, each one has different objective, but all of them have the same thermodynamic cycle, which is, as you can see here. So usually for a refrigeration or a heat pump, I'm planning to heat something. If I'm planning to heat something, this is a heat pump. If I'm planning to cool something, this is a refrigeration cycle. refrigeration cycle مثل ايش؟ مثل الثلاجات. Okay, refrigerators. So you put food, so you want to heat, you want to cool this food. So you extract heat, which is this one here, Qn. So I'm extracting heat from the food. All right, I'm putting it into the system, which is my coolant, for example, and then I'm dissipating heat to the environment outside يا شباب. فلو رحت من عند الثلاجة حطيت يدك ورا الثلاجة بتحس الحرارة. ليش؟ لأن هذه هي الكيو اللي تطلع برا. تطلع برا, والhot environment here is basically the ambient here. Okay. طيب, how can I extract heat من الcool body هذا or cool food, for example, is by applying work. So I'm providing work, or I'm inputting work into my system. So if I want to represent or evaluate the performance of this cycle, is basically, I call it beta here, which is called coefficient of performance. Is basically my desired output, for example, is the Qn. So my desired output is to remove as much heat as possible, okay, over the input, which is the work I'm inputting in order to remove this heat. So it's Qn over Q of the cycle. Again, the QW of the cycle is equal to Q of the cycle, and then I can rewrite this as Q out minus Qn. Q out minus Qn. I'm writing it like this because usually Q out is hotter or more greater than the Qn. So I'm writing it like this in order to avoid a negative sign here. So this is Qn over Q out minus Qn. For the heat pump cycle, objective is different. The objective is to heat this body, is the Q out. Okay, so basically my desired output is Q out in this case, and the input, the same input, which is work of the cycle here. So Q out over work of the cycle eventually is Q out over Q out minus Qn, and this is gamma. Okay, so beta and gamma are called coefficient of performance. So for the power cycle, this is called efficiency, which is theta. I think this is theta or something. So this, for the power cycle, this is called efficiency. For the refrigeration and heat pump cycle, this is called coefficient of performance. Coefficient of performance. Okay. So this is it, يا شباب. That's all what I wanted to mention to you in this lecture. Um, and I wish you all the best. Let me know if you have any questions, and inshallah I should be able to answer you. Good luck, يا شباب. Take care.